ParTools is a toolset designed to help the software developers find better parallelization opportunities faster, increasing their productivity. Most modern architectures are parallel, and parallel execution of the programs is increasingly important to exploit their performance. However, writing efficient parallel programs is challenging, and it's even more challenging to convert legacy sequential programs to parallel execution. ParTools helps the designer in this process. ParTools flow can be divided in two major phases. First, the trace of the program execution is acquired. This includes the execution profile of the program statements, the data dependencies, information about loops, call stacks, and so on. This step is typically done only once. Next, the developer can analyze the trace data to discover parallelization opportunities. The most promising of these can be implemented and tested in parallel versions of the program. To acquire the execution trace, the source code is automatically analyzed and instrumented with calls to the API functions of the runtime trace library. Then, the instrumented program is run using a suitable data set, and the trace data is automatically collected. The trace data is displayed graphically in a compact format that can be incrementally explored, such way to help the developer focus on parallel discovery. Based on this analysis, the developer can decide on different parallelization strategies and implement and test them in the IDE of the toolset. Next, we will demonstrate the operation of ParTools on an MJPEG encoder project. The source code instrumentation is done automatically using a C2C compiler. This analyzes the C sources of the project and generates new source files that include API calls to the tracer library while preserving the original program behavior. The instrumented sources are then automatically compiled into objects that are then linked to create the executable. For projects based on Make and GNU tools, this step can be as simple as replacing the GNU compiler and linker with the compiler and linker provided by ParTools. Here we can see the structure and the files of the MJPEG project. There are separate top-level directories for the C sources, for the object files, for the include files, and for the data files. Also we can see the make file of the project and some project files of the CodeBlocks IDE. The make file has a typical structure. The external commands that are used are defined using variables. We see the compiler and the linker. We can also see the rules for the compilation and for the linking. The project is built natively in the usual way. And to build the instrumented program, we need just to replace the native GNU compiler and linker with those provided by ParTools. We can see that the source file was compiled and linked into the instrumented program. The instrumented source files are removed after the compilation, but they can be preserved by passing the compiler a special option that can be found in the documentation of the toolset. Once we have the instrumented executable, we are ready to collect the execution trace. The instrumented program is run as usual, with an input data set chosen to exercise well the program parts that are interesting for parallelization. Also, the data set should be reduced since the execution of the instrumented program is significantly slower. The trace data collected at runtime are saved at the end of the execution and can be analyzed using the visualization tool. The instrumented program is run as usual, and at the end of the execution it saved the trace data collected. The trace data visualizer is controlled from a menu in the top bar of the integrated CodeBlocks IDE. There are commands to start and stop the visualizer and to load the trace data. The data visualization makes an extensive use of folds. When we open the trace data, we can see a fold of the main function that includes 100% of the program execution and all data dependencies, and it is located in MJPEG part.c on line 5. Most of the graphical elements are connected to the relevant line in the source code. For instance, the top-level fold is associated to the source line where the main function is declared. Folds can be unfolded and their content is added to the current view. We can see that was added a loop fold to the view, represented in a rectangular box. This represents the loop starting on line 19 of MJPEG ParTools file within the main function, and that folds virtually all program execution. The fold of the main function above still holds the statements of the main function that do not start the fold, that is, that do not start the loop and are not calling a function. The colorization of the folds encodes the execution intensity of their statements and all the call stacks they fold. The arrows that connect the folds or statements represent data flows between the statements included in these folds that can be at any level in the call stacks. The color and width of the arrows encode the amount of data exchanged during the whole program execution. In this case, the search for parallelization opportunities may stop here. We can see that the top-level for loop includes a significant amount of execution effort. If it has no loop carry dependencies, its iterations can be processed in parallel. For a detailed view of the data dependencies of the loop, we can use this data dependency view. This view can be generated for any fold. The top layer shows the statements outside the fold under analysis that produce the data that is consumed inside the fold. The variables holding this data are shown in the layer just below, and each is linked to its declaration in the source code. The layer below shows the statements within the fold under analysis that either consume data from outside or produce data that is consumed outside the fold. In this view, a loop carry dependency would appear as a variable that is both consumed and produced within the fold under analysis. Thus, the absence of output data in the data dependency view means that there is no loop carry dependency. Hence, the iterations of the top-level for loop can be processed in parallel. To look for other parallelization opportunities, we expand the fold of the top-level for loop. This uncovers the fold of the initVideoIn function, which includes a negligible amount of execution, and the fold of an inner for loop that holds most program execution. At this point, we can analyze if the inner for loop can be parallelized as the outer one or unfold it further. We have reached now the third nested for loop, which can also be considered for data parallelization. Deciding to unfold further, looking for other parallelization opportunities, we notice that the view is getting cluttered with folds that represent negligible amounts of execution. ParTools offers a graph rerouting function, which allows to select only one fold to be displayed, as if the program execution will have started there. The other folds, which are less important for parallelization, are removed from this and all subsequent unfolds. This allows the developer to focus on the parts of the program that can hold other good parallelization opportunities. Unfolding further, we discover a set of call stack folds that appear to process in sequence a set of data. Namely, the variable called block. Each of these call stacks can be good candidates for tasks in a parallel version of the program. Their data dependencies can be better analyzed using the data dependency view. We can see here other input dependencies beside block that were removed from the previous overview by the graph rerouting operation. Without rerouting, this can be seen in the overview too. ParTools can also insert comments in the source code that list the input and output data dependency for a fold. For the main DCT function, we can insert the comments. These comments contain the input data dependency, the output data dependency, and they also include an OpenMP Pragma template that can be customized by the developer to parallelize the program.